Atoms are tiny particles consisting of electrons, protons, and neutrons, which are in turn made up of quarks. The origin of these particles that make up atoms can be traced back to the Big Bang. Where do electrons get energy to spin around an atom's nucleus? How did the first atom form? There are some of the basic principles that we know about, but what are they in the real universe? How do they act? You and everything around you are composed of countless atoms, estimated to be more than 10 quadrillion vigintillion in the observable universe, which is one followed by 78 zeros. The Big Bang Theory explains the beginning of the universe, where an immense amount of energy condensed, leading to the formation of atoms. However, the process was much more complex than this brief explanation. To understand the scientific perspective of the Big Bang, we need to examine the events in the early universe. Unfortunately, we don't have a definitive understanding of precisely when the universe started, or if it indeed did. Our best model, the standard model of cosmology, allows us to trace back time close to the beginning, but we encounter a barrier at t equals 1. The theory predicts a singularity, a moment of infinite density, where all matter and energy were compressed into an infinitely small point. Most physicists believe this prediction may not be entirely accurate. We can only go back to one Planck time, which is about 10 to the power of minus 43 seconds. Before this moment, we have no knowledge of what occurred. So while we get very close to the beginning, it's not precisely at t equals 1. Understanding the events at this incredibly small timescale requires a quantum theory of gravity, where gravity, which explains the behavior of large objects, meets quantum mechanics, which governs the behavior of particles at tiny scales. This first epoch of the universe, known as the Planck epoch, occurred at 10 to the power of minus 43 seconds. During this time, it is believed that all the fundamental forces, including electromagnetism, the weak force, the strong force, and gravity, were unified as one grand unified force. To create a timeline of the Big Bang Theory, we start before the Planck epoch, setting the clock to 0 at this point. However, it's important to note that this isn't exactly t equals 1, as we want to avoid the singularity. The state of the universe during this epoch and what happened before it remain unknown. The earliest time we can theorize about is the period of inflation, which occurred from about 10 to the power of minus 36 seconds to about 10 to the power of minus 33 seconds after the Big Bang. During this time, whatever existed prior to inflation experienced rapid exponential expansion faster than the speed of light. This is permissible because there's no theoretical restriction on the speed at which space can expand. It expanded from a point to about the size of a large orange. You might wonder how this is possible, since we know that nothing can travel faster than the speed of light. While that's true for information transfer, cosmic inflation involves the expansion of space itself, allowing distant points to move away from each other faster than light can travel between them. Most of our current understanding comes from the period after inflation. So, the accurate way to view the Big Bang is not as a single point of origin, but as a period when the early universe was extremely hot, dense, and rapidly expanding. Thus, the Big Bang is a description of everything that occurred after t equals 1. Inflation is believed to have occurred from 10 to the power of minus 36 to about 10 to the power of minus 33 seconds. The energy source behind this rapid expansion remains unknown, and cosmic inflation erases any information about what existed before it. Where do electrons get energy to spin around an atom's nucleus? An atom is most effectively envisioned as a compact, dense nucleus encircled by rapidly moving orbiting electrons. This concept naturally raises a question. How do electrons sustain their motion around the nucleus without slowing down? This question became a major concern in the early 20th century and led to the development of quantum mechanics itself. During this time, physicists were making strides in understanding atoms and recognized that each atom contained a positively charged nucleus with considerable mass, surrounded by tiny, negatively charged electrons. Armed with this general understanding, they sought to construct a more detailed model. Initially, scientists drew inspiration from the solar system, with a dense nucleus, the Sun, orbited by smaller particles, the planets. However, this model posed two significant issues. Firstly, charged particles that accelerate emit electromagnetic radiation. Since electrons are charged and accelerate during their orbits, they should emit radiation, which would cause them to lose energy and quickly spiral inward to collide with the nucleus. However, atoms are known to exist for much longer than a picosecond, making this model untenable. Secondly, atoms were observed to emit radiation at specific discrete frequencies, unlike the continuous emission expected from an electron following the solar system model. Niels Bohr, a renowned Danish physicist, was the first to propose a solution to these problems. In 1913, he suggested that electrons in an atom could not occupy just any orbit, but were confined to specific quantized distances from the nucleus. He also proposed that there was a minimum distance an electron could reach, beyond which it could not move any closer to the nucleus. Bohr's ideas were not mere conjecture. They were built on the work of German physicist Max Planck, who had proposed the quantization of radiation emission a little over a decade earlier. According to Planck, objects could only absorb or emit radiation in discrete chunks, not in any arbitrary value. These discrete chunks were characterized by a constant value known as Planck's constant, which had units akin to angular momentum. Bohr adopted this concept and applied it to electrons orbiting a nucleus, asserting that the smallest possible orbit of an electron would have an angular momentum equivalent to exactly 1 Planck constant. Higher orbits could have integer multiples of the Planck constant, such as twice or 3 times its value, but never fractions like 1.3 or 2.6. The full comprehension of why electrons possess specific orbits and well-defined energy levels required the complete development of quantum mechanics. Electrons, like other matter particles, exhibit both particle and wave behavior. While we might envision an electron as a tiny planet orbiting the nucleus, we can equally visualize it as a wave enveloping the nucleus. Waves confined within a limited space must adhere to special rules. They cannot have arbitrary wavelengths. Instead, they must consist of standing waves that fit precisely within the space. This is analogous to playing a musical instrument. When you fix the ends of a guitar string, only specific wavelengths produce distinct notes. Similarly, the electron wave encircling a nucleus must fit the available space, and the nearest orbit is determined by the first standing wave of that electron. Future advances in quantum mechanics would continue refining this model, but the fundamental point remains unchanged. An electron cannot approach the nucleus any closer due to its inherent quantum mechanical constraints, which prevent it from occupying a smaller space. However, an entirely different approach to understanding this situation does not rely on quantum mechanics at all. Instead, it considers the various energies involved. An electron in orbit around a nucleus experiences electrical attraction towards the nucleus, constantly being pulled closer. At the same time, the electron possesses kinetic energy, trying to propel it away from the nucleus. For a stable atom, these two forces are in equilibrium. In fact, the total energy of an electron in orbit, which combines its kinetic and potential energies, is negative. Consequently, adding energy to the atom is necessary to remove the electron. This concept, parallels the behavior of planets orbiting the Sun. To remove a planet from the solar system, energy must be added to the system. One way to envision this scenario is to picture an electron falling toward the nucleus due to the attractive electric charge. However, because of the principles of quantum mechanics, the electron can never reach the nucleus, becoming perpetually stuck in orbit. Nevertheless, this situation is permissible according to physics because the total energy of the system is negative, signifying its stability and binding the components together to form a long-lasting atom. So friends, what are your thoughts about this theory and understanding that we have captured until now? Comment your thoughts below, like and share this video with space science enthusiasts, and subscribe to the channel for more similar videos.